All right, let's do this. I told you that I would go over the problems from the lecture in more detail. So here we go. Level 1, we got an inclined plane. It is inclined at 35 degrees. There is a block on it. The mass of the block is 0.8 kilograms. And then at this point, it just barely starts to move. All right, that means that free body diagram time. I got gravity force down. I got normal force up. And I have the force of static friction. Force of friction static. All right, now, not a free body diagram, but infinitely more useful would be this. I got my normal force. I got the x component of my gravity force. I got the y component of my gravity force. And I have the force of static friction. All right, now, I'm going to focus on this. And now I'm going to do some Newton's second law stuff. Because I want to find for the coefficient of static friction. Well, here's what I know. These two are equal and opposite to each other, so I'm just not going to worry about them. And instead, I got the sum of all forces is equal to mass times acceleration in the x direction. That would be Fgx plus static friction equals mass times acceleration. All right, now I got to decide which direction is positive and which direction is negative. I'm going to call this positive and this negative. Again, it doesn't matter. Especially not in this case particularly, because if it's just barely moving, that means that acceleration is 0. Okay, and then static friction force, that's going to be the coefficient of static friction times normal force. And I'm going to subtract that from Fgx, which in this case is mg sine theta. All right, but I'm going to put some numbers in here. 0.8 times 10 is 8 sine 35. Okay, and then my normal force, well, that's going to be mg cosine theta. So I got 8 sine 30. Now, let's go ahead and get the calculator and get the answer for that one, shall we? Go calculator powers. Sine 35 degrees is 0.57-ish times 8. 4.59, I'm going to round that to, minus us times 8 times cosine 35. All right, well, cosine of 35 is 0.819, and that times 8. 6.55. So I got 4.59 minus coefficient of static friction times 6.55 equals 0. Oh, hey, lunch is over. And now I just got to solve for the coefficient of static friction. I'm going to start by adding this over to the side, get rid of that negative. So that gives me 4.59 equals coefficient of static friction times 6.55. Then I'm going to divide both sides by 6.55. And I get my answer of the coefficient of static friction equals, let's see, 4.59 divided by 6.55 equals 0.7. Wait a second, Mr. Sazo. On the slideshow, didn't it say 0.01? Yeah, I think it did. Oh, actually, no. For this one, I just gave you mu tan theta. I'm thinking about a later problem. Okay, so the numeric answer is 0.7. So is that the same thing as mu tan theta? Well, that's easy enough to figure out. Just got to find the tangent of our 35 degrees. Yep. Yay! All right, there we go. Level 1 complete. And here we are in level 2. I got this box here. And it's 20 kilograms. It's being pushed up an incline of 20 degrees. The coefficient of friction in this problem is 0.4. And I'm pushing with 85 newtons up the ramp. And I want to know the acceleration of the block. Okay, well again, free body diagram, which isn't horribly useful, but we're going to do it anyway, because they like to ask you about it. Got the force of gravity, we got the normal force, we got the applied force, which is our 85 newtons. And then we also, of course, got our friction force. In this case, that's kinetic friction. How do I know that? Because it's moving. That's how I know. All right, now, more useful, but not technically a free body diagram. We got our normal force and FGY. We got our applied force. And we got FGX. And then we also got friction force. All right, now, just like in our last problem, this is going to be mg cosine theta, which means this is going to be mg cosine theta. Technically, that's negative mg cosine theta, and this is positive mg cosine theta. We know that this one is going to be mg sine theta. This one is going to be coefficient times normal force. Okay, so we kind of know everything, and we're solving for the acceleration. Okay, well, sum of all forces in the x direction is going to equal mass times acceleration in the x direction. Why didn't I do y direction? Because I know these two got to cancel each other out already. So I'm just not worrying about it. Okay, again, I got to figure out what direction is the positive. In this one, it says that I am pushing it up the ramp. So I'm going to assume that up the ramp is positive, which means I got 85 newtons minus my FGX minus my friction. And that's going to equal mass times acceleration in the x direction. All right, well, 85 FGX, that's mg sine theta. Friction force, that's mu k mg cosine theta, because it's normal force, equals mass times acceleration in the x direction. And now I'm going to start plugging in numbers. I know that m is 20. So this is 85 minus 20 times 10 is 200. Minus mu k, which is 0.4 times 200 times other things that I'll get to later. And this is 20 times ax. All right. Now I need sine of 20 degrees. which is 0.34. And cosine 20 degrees, which is 0.94. And I'm just rounding to 2 decimal places for laziness sake. You got to round somewhere. All right, at this point, look at this. Literally all of this is just numbers. So it's going to be some sort of number is going to equal 20 times my acceleration in the x direction as it goes up the ramp. All right, so 85 minus, okay, well, let's figure out what 200 times 0.34 is. 68 minus, all right, 0.4 times 200 times 0.94, 75.2. Uh-oh, these numbers are pretty big. All right, so all that is going to give me 85 minus 68 minus 75.2 gives me negative 58.2 equals 20 times AX. So this would be my net force, the negative 58.2 newtons. That's my net force here. Which means that although I am pushing this up the ramp, I'm getting slower as I go. Friction is stronger than I am. So although I'm still moving forward for now, I won't be for long. All right, and then this is just mass times acceleration on the right. I'm going to solve for the acceleration by dividing both sides by 20. Divide by 20. And I get negative 2.91. Again, that means that my velocity changes by negative 2.91 meters per second every second. Yay! Here we are, level 3. I got a block. It's being pulled up a ramp by this thing as it falls. At least I'm assuming that's how it's going. Technically, this one could be going down the ramp, and this one could be pulled up. I just straight up don't know. We're going to assume, though, that's my positive direction. Why? Because I got to assume something. So I'm just guessing. All right. What's going on here? Derive an equation for the acceleration. Okay, well, that means I need to know what's going on. Well, let's look at our free body diagrams real fast. Over here, I got a force of gravity and a tension force. This is on the small m. And then over here, I got a force of gravity for the big M. And normal force. And tension force. And if I'm assuming it's going that way, that means friction force has to be counter that. Okay, but that's not horribly useful. So I'm going to look at this and I'm going to turn it into the more useful thing. All right, now when I look at this and this, what I see is a positive force here and here, and then a negative force here, here, and here. So when I look at the sum of all forces in the x direction, now that's going to be equal to the mass of my system times acceleration in the x direction. What I got is Fg little m minus tension force plus tension force minus Fgx minus force of friction. Okay, well, minus tension force plus tension force, that just cancels out. I don't care about that. And now we're just going to start substituting stuff in. All right, well, I know that that's mg. Yay, that was hard. This bit, this is big M, G, but only the X piece. And this is going to be coefficient of friction times mg, just the Y piece. And I want the acceleration. So although it looks ugly, it's really not that bad. You just have to keep track of what you're plugging in where. As long as you remember that this is just FGM, that this is just FGX, that this is just friction force, because this bit right here is normal force, it's easy. It's ugly, it's a lot of writing, but none of these steps are difficult. Because then I divide both sides by mass of system, and I get acceleration of system is going to equal big, long, scary mass, which takes a long time to write, but doesn't actually mean much, divided by mass O system. Yay! Now, the second part for level 3 is, well, how would you find the tension force now? But I've added the term acceleration. So I'm going to go back over here to that free body diagram, and I'm going to write the sum of all forces equals mass times acceleration for just the hanging weight. Because what that gives me is FGM minus tension force equals mass times acceleration. Except I know acceleration. I know mass. Do I know FGM? I do, because it's just mg, and I know m and g. I know everything except tension force, which is good because I'm trying to solve for tension force. So I'm going to add tension force to both sides. Ooh, sorry. Ooh, so sorry. Nope, never mind, we're good. I thought I made a mistake. I thought this was supposed to be mass of the whole system for a moment. But no, it really is just the net force of just the hanging block. So I really just need the mass of just the hanging block. So I'm good there. So I'm going to add tension force to both sides. It's a plus now because I added it. And now I'm going to get rid of the MA. Yeah, so that's tension force is mg over ma. You know, I could cancel out the m's if I want. Now, this one on the slideshow is wrong because I did what I almost did right here. On the slideshow, I made this be the mass of the whole system. That's not true. This is just the mass of the hanging weight. So yeah, the problem on the slideshow is wrong. I'm actually changing it right now. But if you looked at it in class, what you remember is wrong. Okay, there we go. Now we're on to level 4. All right, here we go. Level 4. Whew, we got 2 different angles. This one isn't hanging anymore. Now it's also on an inclined plane. Same friction though. And again, we're solving for the acceleration of the system. Again, that means it's not actually going to be that bad because it's just that. But it's of a system, right? So it's going to be the sum of all forces in the x direction is going to be equal to the mass of the system times the acceleration in the x direction. That's it. I'm just going to solve for A. The only weird bit is I got to, find what all the sum of all the forces are. So let's start that by making some free body diagrams. For little m, sorry. Well, I got a tension force going up. I got a normal force going out. I got a gravity force going down. And then over here, I got a normal force going out. I got a tension force going up the ramp. And I got a gravity force going down. Now, I got to decide on a positive and negative, and I got to decide on what direction it's going. Personally, I always make the forward direction positive, and I have no clue. I honestly have no clue. So I'm going to guess. I don't know what direction it's going to go. I can't know that unless I know these masses. Like, it's impossible to know without knowing these masses. But I'm going to show you how it doesn't matter either. We're just going to assume it's that way and move on with life. Now, again, these free body diagrams are not actually that useful. Sorry, my phone is being weird. Okay, good, we're still recording. So free body diagrams, but they're not that useful. So I'm going to redraw them to be useful. Oh. There's for the one on the left, and then for the one on the right, it's going to kind of be the mirror image of it. All right. So, using this stuff on the bottom, sum of all forces. Well, I see a forward force in this FGX. So FGX for little m. Minus tension force. Plus tension force. Minus FGX for big M. Ooh, except, I forgot to include my friction forces. Oh no. Okay, well, the friction forces are both slowing this down. Oh, sorry, I even drew that in the wrong spot. Bam, there we go. That's what the friction force should be. They're both going in the backwards direction. So I'm just going to do force of friction on little m and force of friction on big M. And that big, ugly mess is going to be equal to this. All right. Minus tension force plus tension force. I don't care. All right, let's start putting things in. Whew. FGX. Okay, that's going to be mg sine of the angle. That angle, because that angle. Little m, because we're talking about this one. All right, now minus FGX on the other side. So big mg, because we're talking about the big M, sine this angle. Okay, no, it's not so bad. Minus friction force. Okay, so that's going to be coefficient friction times little mg, because we're talking about little m, cosine, because we want the normal force, of that angle. And then for force of friction on the other one, it's a big M, because we're talking about big M, cosine theta, because we're talking about this one. All right, equals. All right. God, that is a big, awful, ugly mess. So, doesn't matter. Doesn't matter if it takes me 10 minutes to write it. None of this was hard. It's just a lot of writing. The acceleration is going to be the sum of all forces divided by the mass of the system. So, here we go. Sum of all forces divided by mass of the system. Whew. All right. Mr. Sasso, what if the blocks are going the other way? How does that change things? Yeah, it means that these things would be plus friction because they would be going in the positive direction instead of in the negative direction. So there you go. If you write it like this, you're taking into account the fact that you don't actually know what direction it's moving. And it doesn't matter. You're just saying, hey, you know, it's going to be plus or minus. It's going to be one of those, depending on which direction it's going. Now in the problem, I'd probably actually tell you. All right, so I really hope that although we're acknowledging that, yes, this is so much stupid writing, it really isn't that hard. At heart is this idea. At heart is this idea. If we have an object, this gravity force can be broken into x and y components. So although this is what's really happening, this is our free body diagram, we can pretend that it's that, where these two things have to be equal and opposite, which means the only stuff that we care about as far as acceleration goes is FGX and if there's other forces in this plane of existence. And why is it sine, cosine, and such? That's because this angle theta is equal to that angle of that triangle there, which I could derive for you, but trust me, you don't care. Yay!